Applications of physical simulation in computer science. First, let's start in the introduction. Physical simulation refers to the use of computational models to replicate and study the behavior of physical systems in a virtual environment. By applying the laws of physics, such as motion, gravity, fluid dynamics, and thermodynamics, physical simulations allow us to predict how objects and materials will behave under various conditions. In short, physical simulation is the use of physical objects or computer models to mimic real-world physical processes. Let's move on in the examples of physical simulations. Here we have the visual effects. Physical simulation refers to the use of computer-generated imagery, CGI, to replicate or simulate real-world physical phenomena in a believable and realistic way. These simulations mimic the behaviors of materials, objects, and forces in the physical world to create effects that would be too difficult, dangerous, or expensive to achieve practically on set. We have 6 types of visual effects. These are the fluid, rigid body, soft body E, smoke and fire, cloth and particle system simulation. First, let's start with the fluid simulation D. Fluid simulation D. Simulating liquids like water, oil, or lava. This is commonly used for scenes with splashing, flowing rivers, or magical substances. Next one is the rigid body simulation. Modeling solid objects and how they interact with each other under forces like gravity, impact, or collisions. Next is the soft body simulation. These simulate deformable objects, such as rubber, cloth, and organic matter. It's used for things like fabric movement or character muscle behavior. And here we have the smoke and fire simulation. Simulating gases like smoke, fire, and explosions that interact with other elements in the scene. This requires advanced fluid dynamics to make the smoke or flames look realistic. Next up is the cloth simulation. The movement and behavior of fabric as it drapes, folds, or stretches. This is useful for things like clothing, flags, or curtains. And lastly, we have the particle systems. These are used to simulate things like rain, snow, dust, or sparks. Thousands or millions of tiny particles are manipulated to mimic environmental elements. And for the finishing touch, we have the importance of having visual effects. Physical simulations make impossible or difficult effects look realistic and convincing, making the visual storytelling feel more immersive. These simulations help enhance scenes in ways that physical stunts or traditional practical effects cannot, all while maintaining the illusion of reality. What is VR physics simulation? Virtual reality physics simulation replicates real-world physics using computer-generated environments, enabling natural interactions with virtual objects through gravity, collisions, fluid dynamics, and object behavior. Key components of VR physics simulation. Number 1. Rigid body physics. It stimulates solid objects that don't change shape, as seen in the video where a ball retains its form upon impact. Number 2. Soft body physics. R physics. It stimulates flexible objects like a rubber duck, which compresses when squeezed but regains its shape due to elasticity. Number 3. Collision detection and response. It detects when virtual objects touch or hit each other, and determines their reaction. Number 4. Gravity and force simulation. It applies real-world gravity, friction, and acceleration to VR objects. In the video, it demonstrates the fabric of the space. Number 5. Fluid and particle simulation. It stimulates liquids, fire, and explosions, as shown in the video with over 1 billion particles in motion. Number 6. Haptic feedback and tactile simulation. It uses vibration and force feedback to create realistic touch sensations. In the video, VR laparoscopic surgery allows trainees to feel resistance, texture, and pressure during procedures. Lastly, number 7. Destruction and fracture simulation. It stimulates breaking, cracking, or shattering objects. The video demonstrates a building collapse affecting nearby structures. Now that we've covered the key components, let's discuss why VR physics simulation is so important. Number 1. VR technology provides a level of immersion that cannot be matched, putting users directly in simulated environments. This intense immersion enables more interactive and effective learning. Number 2. Safer training environments. Safety is a top priority when it comes to real-world training, particularly in risky professions. VR offers a safe platform for learners to practice without risking major accidents or injuries. Lastly, we have number 3. VR training also has the potential for real-time feedback and full analytics. As trainees move through simulations, their movements can be followed and analyzed, providing immediate insight into their performance. Games and entertainment. Virtual reality is being applied more and more in the entertainment and gaming areas, with the user getting a more interactive and immersive experience, which raises the engagement level. Apart from gaming, VR is revolutionizing the way people watch media, with virtual cinemas offering a better screen experience, and virtual concerts allowing users to see live events from any location on the globe. Now, for the last slide of virtual reality physics simulation, I embed video clip of VR game, which is Slender. It showcases a VR horror game called Slender, which is based on the popular game Slender, the 8 Pages. This game immerses players in a terrifying environment, where they must navigate dark surroundings, while avoiding the mysterious and eerie figure known as Slenderman. There are many applications of VR physics simulation, but for now, we will only discuss games and entertainment. Thank you. As part of NASA's Mars Science Laboratory mission, Curiosity was the largest and most capable rover ever sent to Mars when it landed on August 5, 2012 inside the Gale crater. Curiosity was built by NASA's Jet Propulsion Laboratory, which is managed by Caltech in Pasadena, California. JPL leads the mission on behalf of NASA's Science Mission Directorate in Washington. Curiosity's mission aimed to determine whether Mars ever had an environment capable of supporting microbial life. Determining past habitability on Mars gives NASA and the scientific community a better understanding of whether life could have existed on the red planet and, if it could have existed, an idea of where to look for it in the future. Curiosity explores Gale crater and acquires rock, soil, and air samples for onboard analysis. The rover is about as tall as a basketball player and uses a 7-foot-long arm to place tools close to rocks selected for study. Curiosity's large size allows it to carry a kit of 10 science instruments. It has tools including 17 cameras, a laser, and to study small pinpoint spots of rocks, and a drill to collect powdered rock samples. Mastcam, a camera that takes color images and color video footage of the Martian terrain. Mars Hand Lens Imager, a camera that provides Earthbound scientists with close-up views of the minerals, textures, and structures in Martian rocks. Mars Descent Imager, a camera that took color video during the rover's descent toward the surface, providing an astronaut's view of the local environment. Alpha Particle X-ray Spectrometer, a spectrometer that measures the abundance of chemical elements in rocks and soils. Chemistry and Camera, an instrument that first uses a laser to vaporize materials, then later analyzes their elemental composition using an onboard spectrograph. Chemistry and Mineralogy X-ray Diffraction, an instrument that identifies and measures the abundances of various minerals on Mars. Sample Analysis at Mars Instrument Suite, a suite of instruments that searches for compounds of the element carbon that are associated with life and explores ways in which they are generated and destroyed in the Martian ecosphere. Radiation Assessment Detector, an instrument that measures and identifies all high-energy radiation on the Martian surface, such as protons, energetic ions of various elements, neutrons, and gamma rays. Dynamic Albedo of Neutrons, a pulsing neutron generator that is used to detect water content as low as 0.1% and resolve layers of water and ice beneath the surface. Rover Environmental Monitoring Station, an instrument that measures and provides daily and seasonal reposts on Martian weather. NASA's Curiosity Mars rover has collected 42 powderized rock samples with the drill on the end of its arm. Each hole is over a half-inch wide. The images were captured by the Mars Hand Lens Imager. After drilling a sample, the powderized rock is trickled into instruments inside its belly that can analyze the composition of the rocks. Those instruments include sample analysis at Mars and chemistry and mineralogy. NASA's Curiosity rover remains operational and continues exploring Mars as of March 2025. It remains active in its mission to study the planet's geology and past habitability. NASA regularly provides updates on Curiosity's progress, discoveries, and status on its official website. Another example of physical simulation is robotics motion simulation. Robotics motion simulation is a virtual environment where robotic motion and interactions are tested before deployment. It helps refine motion planning, obstacle avoidance, and kinematics. Why is robotics motion simulation important? Robotics motion simulation is crucial for reducing costs, accelerating development, and ensuring safety. It minimizes expenses by replacing physical prototypes with virtual testing, cutting material wastage and labor costs. Simulations also speed up development by allowing rapid testing of multiple designs without manufacturing delays. Additionally, they enhance safety by identifying potential failures before real-world deployment, which is essential in high-risk applications like autonomous driving and robotic-assisted surgery. One of the most widespread applications of robotics motion simulation is in industrial automation, where robotic arms and automated systems perform precise assembly, welding, and packaging tasks. Simulations help engineers design, test, and optimize robotic arms used in manufacturing lines, reducing errors and increasing efficiency. For example, automobile manufacturers use robotic simulations to fine-tune robotic arms for assembling car parts, ensuring precision before real-world implementation. Robotic simulation also applies in autonomous vehicles. Self-driving cars rely heavily on motion simulation to test and train autonomous systems before they hit real roads. These simulations recreate urban and highway environments, allowing developers to train AI algorithms in realistic scenarios involving traffic flow, pedestrian behavior, and unexpected obstacles. For instance, companies like Tesla, Waymo, and Uber use simulation platforms to test their self-driving technologies under different weather conditions, lighting environments, and road layouts. By running thousands of virtual tests, autonomous vehicle systems learn how to navigate complex road networks, respond to hazards, and optimize route planning without risking real-world accidents. This significantly accelerates the development and safety validation of autonomous transportation. In the field of healthcare, robotics motion simulation plays a critical role in training robotic-assisted surgery systems. Surgeons and engineers use simulation software to refine robotic surgical procedures, ensuring high precision in operations such as laparoscopic surgery, orthopedic procedures, and neurosurgery. For example, the Da Vinci surgical system, a widely used robotic-assisted surgical tool, benefits from simulations that model human anatomy, allowing surgeons to practice complex procedures with realistic tissue interactions, organ movement, and tool responses. This enhances surgical accuracy, reduces patient risk, and allows medical teams to gain expertise before performing live operations. The last example for physical simulation is weather and climate simulation. An example of weather and climate simulation is the Global Forecast System. What is Global Forecast System? The Global Forecast System, GFS, is a numerical weather prediction model developed by the National Oceanic and Atmospheric Administration (NOAA). It uses advanced physics-based algorithms and real-time atmospheric data to predict weather patterns worldwide. The GFS operates on a global scale, making it one of the most widely used forecasting systems for meteorology, disaster preparedness, and scientific research. Why Global Forecast System is important? It provides global coverage. Unlike regional models, the GFS delivers weather predictions for the entire world, aiding international forecasting efforts. Predict extreme weather events. It helps in early detection of hurricanes, storms, and other severe weather conditions, allowing for timely disaster preparedness. Support multiple industries, from aviation and maritime navigation to agriculture and energy management. GFS forecasts are essential for planning and decision-making. Enhance climate studies. Scientists use GFS data to analyze climate trends and improve understanding of long-term atmospheric changes. Key components of GFS: data collection. Gathers atmospheric data from satellites, weather balloons, ground sensors, and radar to track temperature, pressure, humidity, and wind patterns. Data assimilation. Integrates and corrects raw data to improve forecast accuracy by combining observations with past predictions. Numerical weather prediction. NWP. Model LAIH uses mathematical equations to simulate atmospheric behavior, predicting changes in weather patterns. Grid system divides the Earth's surface into a network of points to calculate weather conditions for localized forecasts. Forecast output CA generates predictions up to 16 days ahead, updating every 6 hours for accuracy and reliability. The applications of Global Forecast System weather forecasting helps meteorologists predict short and long-term weather patterns, allowing businesses and communities to prepare for changing conditions. Disaster management assists governments in tracking severe weather events, enabling timely warnings, evacuations, and disaster response efforts. Aviation and maritime navigation provides airlines and shipping industries with data on wind, storms, and pressure to optimize routes and ensure safety. Agriculture planning helps farmers determine optimal times for planting, irrigation, and harvesting to protect crops from extreme weather. Renewable energy optimization supports wind and solar energy industries by forecasting weather conditions affecting power generation. Climate research and environmental studies (CLISAMAID) aids scientists in analyzing climate trends, helping shape environmental policies and conservation efforts. The Global Forecast System (GFS) remains a critical tool in meteorology and environmental science, providing accurate and timely weather predictions that influence global decision-making. Artificial intelligence has the potential to transform the social interactions in educational contexts among learners, teachers, and technologies. It has the potential to bring about positive changes in our society. AI-powered technologies make our daily lives easier and more convenient. Simulations help connect theory with real-world practice by providing a realistic environment where people can develop skills. When combined with AI, these simulations become even more effective, enabling faster skill building at a larger scale and lower cost. Physical simulation is important in many areas, helping to model, test, and improve systems before they are used in real life. It enhances movie effects, makes virtual reality more immersive, and improves robotics and space exploration. Weather and climate simulations also help predict future conditions. As technology improves, physical simulation will continue to make industries safer, more accurate, and more efficient.